So this next bit is about communicating. Let's supposing I've got two ships and they can only communicate with each other once they're within a certain distance of each other. So this is moving off in that direction, maybe that's moving off in that direction. So once they're within a certain range, we say they can communicate with each other. So once they're within that circle, communication can happen, or visibility can happen, or whatever. Now, let's apply this kind of idea to the next few couple of questions. I'm looking at question 6 on the sheet. And what we have in question 6 is P is a ship that's 350 kilometres due east of Q. So P's there, and there's Q. There's 350 kilometres between them. The velocity of P, I'm told, is minus I plus j. And the velocity of Q is 3I minus 2j. Okay, I've got to find the velocity of Q relative to P. We'll do that first. That's the relative velocity. So this will be 3I minus 2j minus I plus j. And I'll put them in brackets so that I don't make a mistake with the signs. So this will be 3I minus I will become, of course, 4I. And minus 2j minus plus 1j, that will give me minus 3j. Okay, so that's the velocity of Q relative to P. Even if I wasn't asked for the next part, I would find it anyway. Part 2, so that's part 1. Part 2 says find the velocity, the magnitude and direction of velocity of Q relative to P. So even if I wasn't asked to find that, I would go ahead and do it. So the VQP is the square root of the I component squared plus the j component squared. And of course that's going to be 16 plus 9, 25. So that's going to give me 5. And I'm going to assume, of course, this is all going to be kilometres per hour because the distance is in kilometres. Now, the direction of this. So this is my vector 4I minus 3j. I'll just sketch it here. 4I minus 3j would be going down the page in that kind of a direction. So if I was to draw a right angle triangle around that, that would be my I component and j component. And the angle, of course, would be here. So that angle here, the angle that it makes with the positive sense of the I-axis, I'll call that angle alpha. So the tan of alpha would be the opposite over the adjacent, which would be the j component over the I component. 3 over 4. And I wouldn't bother about the sign here, simply because I can tag it east and south, so that will get rid of any problems with signs for me. So the arc tan 3/4, when I put that into the calculator, I'll get alpha to be 36.87 degrees. And then if I give it an actual direction, it's heading east and then it's going south. So it's east 36.87 degrees south. So that's this direction. Now, the shortest distance. Let's find the shortest distance between those ships. Okay, so here's my diagram. I have Q at the junction, or the intersection, we'll say, at that position there on my IJ axis, the origin. And now I have P over here. I don't have to move any of them to the junction, because to the origin, because Q is already at the origin. So in this particular case, I'm going to put in the relative velocity line, which is this one here, the 4I minus 3j. It's heading down in that direction, and I'm going to put it passing through Q. I'm going to put it coming down like this. Okay, I'm going to drop a perpendicular from P down onto that relative velocity line, and that's going to be my D, and that D is the closest distance. Okay, so I have the angle here. This is the angle that the relative velocity line makes with a positive sense of the I-axis. I'm going to call that alpha, which of course is this angle up here. So I know what alpha is. It's 36.87 degrees. So to find D, remember the sine of alpha would be D over this distance here, which is 350. That's the one I know. That's my hypotenuse. So therefore that means that the closest distance is going to be 350 times the sine of 36.87. And when I work that out, I get 210 kilometres. Okay. Now the last bit is the extra bit, the communicating bit. it says these ships can, we'll say Q and P, they can exchange signals when they are within 290 kilometers of each other. For how long can they exchange signals? Okay, so I'm going to take this diagram again, this one here with my relative velocity line on. That's the one I'm interested in. This is my relative velocity line, this is what it will all be about. This is where P is at the moment. P is up there, Q is there. Okay, so to find, we'll say the length of time through which they can communicate, remember, time is going to be distance over speed. And in this case, it's all coming from the red line again. So it's relative distance over relative speed. Okay, relative distance over relative speed. This is my closest distance, D. So what I'm going to do, they can communicate once they are in 290 kilometers of each other. I'm going to draw a circle around P with a radius of 290 kilometers. And that circle will will touch, obviously, the relative velocity line in two places. So this distance here is 210. I know that after finding that. So if I draw we'll say a circle around here, like that. Okay, so once they are within that distance, they can communicate with each other. Okay, so now, and this, remember, if P is there, this is where Q is relative to it. So I now, from this position at P, I'm now going to draw a line connecting P to the relative velocity line where the circle touches it. So I'm drawing a line from P, I'll do it, sorry, in a different colour, girls, from P to the relative velocity line. And again, I'm going to do it the same on the other side. So this, I'm going to take it from P to where it touches the relative velocity line. And that distance there will be 290 kilometres, and this will be 290 kilometres. Okay, I'm just going to move this up a moment. Sorry, excuse me. You see that? Right, so I'm just going to lift now this triangle from this diagram. So this of course is my red line. That's my relative velocity line, my VQP. Okay. So this distance here is 290. This distance is 290. And of course I know what that is, that distance there, that D. I'm after finding that already, that's 210. And remember, this hit that red line at right angles. So this is 90 degrees here. Okay, so the time we said was the relative distance over the relative speed. The relative distance on the relative velocity line and the relative speed of the relative velocity line. So it's all about the red line again. So if I could get these distances here, if I could find x, because there's two identical right angle triangles, 290, 210, x, 290, 210, x. So these two distances here have to be the same. So the relative distance is the distance on the red line, which is x plus x, divided by the relative speed, which is the distance or the relative speed of VQP, which I already have. So the time, the length of time for which they can communicate with each other will be 2x over, now I know what VQP is, I'm after finding that already, it was 5 from the first part. So my job is to find x, and of course using Pythagoras I can find x pretty easily. So if I say 290 squared minus 210 squared will give me, the square root of all that will give me x. And when I put that into my calculator, I get x to be 200 when I use Pythagoras. So the time is equal to 400 over 5, which is 80 hours. So those two ships can communicate with each other for 80 hours.